Let's go. So we are having. We're gonna go through. We're gonna skip. This was a cut to this because I need to lock in for a little bit of ionic equations before we continued for the oxidation of alcohols because I need to. So let's go through this a bit. So if we're talking about electron half equations for oxidation reduction processes, which is basically why we're here for the oxidation specifically, we need to learn how to combine them to give the overall ionic equation for a redox reaction, and it's important skill in organic chemistry. We are doing this for this is for inorganic chemistry. Although we are doing this for organic chemistry, hold up, one sec. Just trying to fix the audio for you guys. Hopefully that's not too loud. Alright, that's perfect for me. So, I mainly want to use this for understanding, stuff like oxidizing agents and stuff. And also for when, electrons half equations usually come up in a chapter. For example, we can literally open it and see it right here. We can see the, the electron half equation over here. And we can also see, a kind of simpler version of it over here with an oxidizing agent over here. So I would like to just be able to go through it and feel less unconfident while reading it. I know it's not too difficult, but still I would like to go through it. So, yeah, see over here, it is a fairly slow process even with experience, so just take your time and practice as much as you can. So, here we have electron half equation, and so when magnesium reduces hot copper oxide to copper, the ionic equation is Cu2 plus Mg, so you're having copper oxide 2, which is hot, plus your magnesium, and it turns into copper, mainly the copper solid, plus Mg2 plus ion, okay? So, it reduces hot, so when Mg reduces hot copper into copper, so we're saying that Mg is the reducing agent, and copper is getting reduced to this. Okay, so I'm gonna leave out the blah 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 because it's awkward enough anyway without having to worry about state symbols. Practice those equations right away and then add the state symbols. Alright, so now you can split the ionic equation into two parts, right? And you can make it look like, from the point of view of the magnesium and the point of view of the copper separately. And this shows that the magnesium has lost 2 electrons and the copper has gained 2 electrons, okay? And these equations are described as electron half equations are ionic half equations, or half equations are electron half equations, and blah blah blah. Any redox reaction is made up of 2 half equations. In one of them, electrons are being lost, which is an oxidation process, as we know. Oil is lost, reduction is gained. So when electrons are being lost, oxidation process is happening. When electrons are being gained, a reduction process is happening. And as you can see over here, electrons are being gained, electrons are being lost, right? So this is going to be your oxidation, and this is going to be your reduction. So again, that's why they stated over here, magnesium reduces hot copper oxide, aka copper oxide gets reduced. So over here, I'm fine on what redox reactions are in terms of electron transfer. Working on electron half equations and using it to build ionic equations. Here is the tough part. So in the example above, we got electron half equations starting from the ionic. We've got at the electron half equations by starting from the ionic equation and extracting the individual half equations from it. That's doing everything entirely the wrong way around. In reality, you most likely start with the electron half equations and use them to build the ionic equation. Now, the reaction, let's take for example, chlorine and iron 2 ions. So chlorine gas oxidizes iron 2 ions into iron 3 ions, aka iron 2 ions will lose more electrons into iron 3 ions. A process that the chlorine is reduced to chloride ions. So we have chlorine gas and it's going to be reduced as it gains electrons to form chloride ions. Right? Now, you would have to know this or be told by an examiner. In building equations, there's quite a lot that you can work out as you go along, but you have to start from somewhere. So you can start by writing down what you know for each of the half equations. In chlorine case, you know that chlorine as molecules turn into chloride ions, so you can write Cl2 into Cl minus. As it says that you're going to be reducing your chloride ions, so your Cl2 is going to be forming Cl minus ions. The first thing you can do is balance them. So you can find Cl2 into 2Cl minus. Always check that you have the existing atoms balanced before you do anything else. Because if you forget this, everything else that you do afterwards can be a complete waste of time. So now, you have to add certain things to the half equation in order to make it balanced. You are allowed to add electrons, water, hydrogen ions. Now, hydrogen ions is unless the reaction is being done under alkaline conditions in which you add OH ions instead. I remember doing this in class. Now, in the chlorine case, all that is wrong with the existing equation is that we've produced so far won't balance the charges. The left hand of the equation has no charge, whereas the right hand of the equation contains two negative charges. So, simply, we can just add in two electrons on the left hand side. That means the final version of the half equation, fully balanced in terms of charge and in terms of number of atoms, is going to be this. Now you repeat this for the iron 2 ions. You know, or you're told that they're going to be oxidized, so they lose. So you can write Fe2 plus into Fe3 plus. However, the charges don't balance, but the atoms do. So you just want to balance the charges. So there's 3 positive and 2 positive. So you can just add in a negative on the right side to balance it. Now, when you've combined half equations, now you want to combine half equations to make the full ionic equation for the reaction. Okay. So what you've got at the moment is you have Cl2 plus 2E minus is equal to 2Cl minus because it gets reduced. And you have Fe2 plus into Fe3 plus E because it gets oxidized. Now, we have a main difference here. Your 2E and your E is going to be different. You're going to have two E's which are needed and you only have one E that's produced. So it's obvious that the iron will have to be happening. The iron reaction, this bottom one, the oxidizing one, is going to happen. It will happen twice for every chlorine that happens. Allowing for that, we can add two half equations together by multiplying the bottom and then multiplying the bottom by 2 and then adding them together. So after you've multiplied the bottom by 2, that will be 2Fe, 2Fe3 plus 2E. Now you add in the 2 electrons, you're going to have Cl2, 2Fe2 plus, 2Cl minus, and a 2Fe3 plus. That's going to be your first thing. Now, just letting you know, you've balanced the electrons, which means that you're going to have 2E going into here and forming 2E, which means that 2E was never there in the first place. I mean, it is, but you could just remove it because it's an ionic equation. It doesn't need to be there. Right, you can literally just remove it because there's going to be 2 here, 2 here, 2E, 2E, and it's going. So, in reality, you have your 2E minus over here and your 2E minus over here, but in reality, I mean, if it's going to be on both sides, it's spectators, so it doesn't need to be there. Now, you don't need to stop here. Check everything balances, atoms and charges, and it's easy to make a small mistake, especially if you're trying to multiply and add up more complicated equations. So, the final equation is going to be Cl2, 2Fe2 plus, 2Cl minus, and 2Fe3 plus. You'll notice that I haven't bothered to include the electrons because if you think about it, they're bound to be the same number on each side, so they'll cancel out. And if you aren't happy with this, write them down and cancel them out afterwards. We have a more complex reaction. The first one, which is a simple bit of chemistry that you'll probably come across. The technique just works as well for more complicated and unfamiliar chemistry. Now we have MnO4 minus, and which oxidizes hydrogen peroxide H2O2 to oxygen gas. So H2O2 gets oxidized, so it loses electrons to form oxygen gas. And so a manganate will be reduced, so it will gain electrons further. The reaction is done with potassium manganate solution and hydrogen peroxide solution acidified with diluted sulfuric acid. Okay, so since it's an acid, we can add H plus ions, and it's hydrogen peroxide solution. The reaction is done with potassium manganate, so it's going to be potassium. So we said that manganate ions get reduced and hydrogen peroxide gets oxidized. Now you're not going to just have manganate ions and hydrogen peroxide just available. You're going to get this from hydrogen peroxide solution and potassium manganate solution. Okay, why are we diluting this with sulfuric acid? I'm pretty sure that's to have excess H plus ions so that the reaction can continue. But anyways, let's go. So during the reaction, your manganate ions are reduced to manganese 2 ions. So they've stated that. So we can start off with the hydrogen peroxide half equation. hydrogen peroxide half equation, what we know is H2O2 and it goes to O2 gas, and the oxygen is already balanced. So what about the hydrogen? Hydrogen is going to get so we're missing the hydrogen, right? And we know that there's excess H ions over here. So if you're allowed to add in the equation, what you're allowed to add into this equation is water, hydrogen ions, and electrons. Again, in alkaline solutions, you're going to add in OH ions instead of the hydrogen ions. If you add water to this to supply the extra hydrogen atoms on the right side, you'll mess up the oxygens again, which is obviously wrong. You can add in 2 hydrogens instead to the right side to balance the equation. Now all you need to do is balance the charges. So we know that there's going to be H over here, and there's no H over here. So we can add in an E minus over here to balance it. Well, we have 2 H pluses, so that means we need 2 E minuses to balance it. Now for the manganate half equation, we're told that it turns into from manganese 7 to manganese 2. So we can write that as MnO4 minus to Mn2 plus. That's what it's going to be looking like. Because you have manganate, which has O, and you have manganese, which is itself, and 2 plus is just 2 plus. And O4 minus, this is something I don't know. I'm pretty sure they would just tell you it, but anyways, that's a problem for another day. So manganese balances, but you need 4 oxygens on the other side, and these can only come from water, and that's the only oxygen containing thing that you're allowed to write into these equations in acidic conditions. Okay, anything else would not be allowed in acidic conditions, or else you would either be, neutralizing it, or you would be doing something to the acidic conditions, which would just break this entire reaction. So you are allowed to add water. Okay, so now you add in water, 4H2O, and now for H2O you have noticed that you have 4 O's and 4 O's on this side, so the O's are balanced. But by doing this, we've added some hydrogens, 8 entirely to the right side. To balance these, you'll need to add 8 hydrogens on the left side as well. So now we have 8 and 8 hydrogens, 4 and 4 oxygens, and now we just need to, now all the ions are balanced because we have Mn and we have Mn over here. We just need to balance the charges. At the moment, look at the net charges on the left and right side, okay? If you look at the left side, we have 4 minuses and 8 pluses. That gives you a total of, am I going crazy? They said there are net 7 charges on the left side, 1 minus and 8 pluses. Oh, that's my fault. So you have 8 pluses and 1 minus. O4 minus. It's literally not, it's not O minus 4, it's O4 minus. So that means it's going to be 1 minus 7. Minus 1 plus 8 is going to give you a total of 7 plus. Over here, you're looking at a 2 plus, and that's it. Okay? So you have a 7 plus and a 2 plus, which means that you need 5 E minus on this left side to reach that total equal charges. So this is the typical half equation that you will have to be able to work out. Sequences usually start with balancing the atoms between hydrogen, oxygen, and hydrogen, apart from oxygen and hydrogen. So your actual inorganic elements, you want to balance those. Then you want to balance the oxygens by adding water. Then you want to balance the hydrogens by adding hydrogen ions, and then you want to balance the charges by adding electrons at the end. Now the final step is to combine these two half equations to get that final ionic equation for the reaction. So we have MnO4, 8H plus 5E minus Mn2 plus 4H2O, and then your second equation that we did first was H2O2 plus O2 plus 2H plus 2E. Now we just need to balance these 5E's, so we're going to add in 2 on the top and 5 on the bottom, and the end we're going to have this, the crazy guy, 2 MnO4 minus 16, because 2 times 8 is 16, 2 times 5 is 10, and then 5 times 2 is 10, so forget about the E's, they're cancelled now. 2 plus Mn2 plus, 2 plus 8 H2O, then we have 5 H2O over here going down straight because H2O is not located here, and then we have 5 O2, and 5 plus times 2 is going to be 10 H plus, but we're not quite finished because during the checking of the balancing you should notice that there are hydrogen ions on both sides of the equation. We have 10 over here and 10 and 16 over here. We also have is there anything else? No, we're good. We're good because there's H2O2 on the left side and H2O on the left side, so right side, so it's great. Now since we have 16 and 10, we can simplify just by subtracting 10 on both sides to get the final version of this equation. 6H on the left and 0 on the right of H plus ions. And don't forget, to check the balancing of the atoms and charges, you'll often find that hydrogen ions or water molecules appear on both sides of the equation. in complicated cases built up in this way. Always check and then simplify where possible by subtracting in the final equation that we're talking about. In the other equations, like let's say when you're finally combining those two half equations together, you want to be multiplying. You want to be looking at those electrons for that. So now we have the oxidation of ethanol by acid potassium dichromate. First of all, we're talking about oxidation of ethanol, okay? This is actually very related to what we're going to be doing here, which is very cool, but let's keep going. Oxidation of ethanol means that ethanol is going to be losing electrons, okay? By potassium dichromate, that means probably your potassium is going to be reducing it, but let's see. This can work with organic chemicals as well, which is exactly what we're doing. Bingo was his name out, type shit. We're getting organic chemicals. Now, potassium dichromate solution, acidified with dilute sulfuric acid, is used to oxidize ethanol. So we're having two reactants here: potassium dichromate solution, acidified with dilute sulfuric acid. Now, since we're having dilute sulfuric acid, you can imagine H plus ions are going to be in excess, and we have potassium dichromate solution, which we aren't given what happens, but we are given that your ethanol is going to be oxidized into this. Okay. Now, both of these are not ions. Both of these are, they're chill. But we are stated that the dichromate ion is going to be the oxidizing agent, which means it oxidizes ethanol, correct? And it gets reduced, of course. Oxidizing agent gets reduced as the reducing agent gets oxidized. So we have the oxidizing agent Cr2O72 minus, and it's reduced to Cr3 plus only. Okay, that's it. From here to here it goes. And we'll do ethanol to ethanoic acid half equation first. Okay, and then there's no order to it, but since we know, and since there's no electrons involved here, why not? So you have this going to this. Now you want to make sure all the oxygens are balanced first by adding a water molecule. Over here we have CH3, so let's look at the H ions, look at the Ca ions, and look at the I don't know why I keep on saying ions, but COH, okay. We have 2, we have 6, we have, we have 6, and we have 1. If you look on the other side, COH, we are at 1, 2, we are at 4, okay, oops, this is 6, and this is 1. We are at 2 oxygens, we are at 4 hydrogens, alright? Simply put, we just need a very weird amount of stuff on both sides. Simply put, if you put a H2O on the left side, okay, that's gonna give us, an 8 over here, and that's gonna give us a 3 over here. And if you put in 4 H plus ions on the other side, well, guess what happens? That's not gonna be, it's gonna be 2 and 8. And if you add in 4 H plus ions, well, check it out. We'll have 8, 2, 2, 8, 2, 2, 8. We have 2 here. If I said 3, that's my bad. So that's your final equation. You're gonna have not your final equation. This is gonna be where we at right now, and now we just have to put in the charges. And since there's no charges on the left side, we just need to add 4E minus. Now the dichromate half equation contains a trap, which a lot of people fall into. We can start by writing down what you know. Now we know that it gets oxidized. Hold on. Rig is gain, why is it turning positive? What? Okay, this is kind of interesting. So what people often forget to do is balance the chromiums. If you don't do that, you're doomed to get this answer wrong at the end of the process. See, when you balance the charges, you have to you will have to write in the wrong number of electrons, which means multiplying the factors will be wrong when you come to adding the half equations. So first you want to balance the oxygens. So you want to add in those 7 O's, so you want to add in those 7 H2O's. After you've added those 7 H2Os, now you have 14 H's on the right side and none on the left side. So you added the 14 H pluses on the left side. Now just check out check out the the net charges. So we have 072 minus. So you have a 2 minus and a 14 pluses. So that's gonna be your 12 pluses. And over here you have your 2 times 6, 6 plus on the right side. So we're gonna have 12 plus 6 plus. So obviously we're gonna need 6 minus on the left side, and that's gonna be your final equation. See, higher CR2 07 minus 072 minus is turning to CR3 plus. You might notice that okay, fine. If I'm adding electrons, isn't the negative charge only going to get bigger? But in reality, since you're losing your O, if you're losing your, you have 7 oxygens added onto that, and it's having to share electrons with that with those 7 oxygens. When you remove those oxygens, it's going to gain a lot of electrons. Okay, it's going to gain a lot of electrons, aka it's going to get reduced. Anyways, you can think of it as being the opposite of oxidation. It's being reduced. It's losing that oxygen, so it's being reduced, as you can see over here. So, anyways, I know it's a bit confusing, but whatever. What we have so far now is going to be your your ethanol with your water, giving you that carboxylic acid, 4H, 4E, and then we have this equation right here, being right here, your little chromate, dichromate, 14H plus 60 minus to balance the charge, and the 2Cr and 7H2O. And what are the multiplying factors of the equation time? Well, as you can see, the electrons, the simplest way is to find the smallest number of electrons. So if you do 4 divided by 12, that's going to be multiplying 1 by 3 and 1 by 2. Top equation by 3, bottom equation by 2, to give both of them a total of 12 electrons. So then, your 3 CH2, your 3 ethanols, 3 waters, 3 ethanoic acids, and your 12 H pluses, 2 CR2s, whatever, 28 H pluses, 4 CR3 pluses, and 14 H2Os. You're going to add them all together, and you're going to notice that before you're adding them together, you're having H2Os over here, H2Os over here, H pluses over here, H pluses over here, and that's going to be it. So you want to subtract it, get rid of all the H2Os over here, and get rid of all the H2Os over here, turn this into 11, get rid of all the H2Os over here, turn this into 16. So you have your final equation like that. Now, simply put, this is the last part. Reactions by half equations, okay? Sorry, let's just read this. Now you've seen a cross-section of this sort of equations, which could be asked. Now you need to practice that so you can get it pretty reasonably and quickly accurate. Aim to get an averagely complex problem done in about 3 minutes. If you want more and the opportunity to practice, you might be looking at chapter 1 of my chemistry book. We will go through that hopefully in a bit. Not today though. Working out half equations for reactions in alkaline solution is decidedly more tricky. You are less likely to ask about what to do in this level, and for that I've covered this on a separate page. It'll be worthwhile checking the syllabus and past papers. Are you kidding me? Oh my god, I want to be done with this. How long is this shit? Dog. Okay, most of this is equations, so I don't mind. Plus, alkaline solutions is like, I swear, it's the annoying part, trust me. So let's just go through this. I've been popping bottles. Whoa, sorry about that. Okay, here we go. Indeed. Okie dokie. So we have alkaline conditions now, and we're looking at oxidation reaction fractions that are specifically for those conditions, and then combine them to get that overall ionic equation. Combining them is easy, working them out may be more or less difficult than under acidic. Now, why is it more difficult? Well, What you already know is, when you're trying to balance half equations, you're only trying to add water, electrons, and hydrogen ions. But unless the reaction is done under alkaline conditions, then you can add hydroxide ions instead. If you're working under acidic or neutral conditions, then the sequence is usually balancing the atoms other than oxygen and hydrogen, then balancing the oxygens by adding water, balancing the hydrogens by adding hydrogen, and balancing the charges by adding electrons. The whole process is fairly automatic, and provided you take care, there isn't much wrong to go. How is it different under alkaline? Well, as it said, the water and hydroxide ions that you add to balance the equations under alkaline conditions contain hydrogen and oxygen. See, H2O and OH minus. When you balance the oxygens, you could, in principle, add either H2O or OH minus to the equation. The same thing is true for balancing hydrogens. How do you know what to start with? This is how to tackle the problem. In some cases, it's obvious to build up the half equation using hydroxide ions. Always check this before you get involved in anything more difficult. You'll see what I mean shortly. If it isn't immediately obvious, then work out the half equations as if it was being done under half acidic conditions, just as you learned to do it on the previous page. In other words, writing in water molecules, hydrogen ions, and electrons. Once you have the full balanced half equation, then you convert into alkaline conditions. You'll see how to do that. 4 examples. Don't worry if the chemistry in these examples is unfamiliar to you. It doesn't matter in the slightest. It all matters is how you work out these equations. So we're oxidizing cobalt to cobalt 3 by hydrogen peroxide. We have an excess of ammonia solution, so the solution is ammonia, that's going to be our solvent. To a solution containing cobalt 2 ions, you get a cobalt. Sorry, that's not going to be actually whatever. Yes, it's going to be solvent as well. So you're going to be your final thing that you're going to be making is going to be your complex ion called hexamine cobalt 2 ion. Wait, hold on. Yeah, and then that's rapidly reacting with the hydrogen peroxide solution. This is oxidized rapidly by hydrogen peroxide solution to the ion, 3 ion. So all that happens is it's getting oxidized, so it loses an electron. Goes from 2+ to 3+. Your hydrogen peroxide is going to be the thing that reduces it, which oxidizes it. So your hydrogen peroxide, of course, is going to get reduced. However, your ammonia solution is where your reaction is taking place. Your ammonia solution is where your cobalt 2 ions is going to be turned into CONH 362+. And yeah, it's an alkaline solution. The half equation for the cobalt is easy. Write down, what you know. And simply everything is balancing except for the charges, so you add in that E minus. Now, the hydrogen peroxide half equation isn't very difficult either, except for the fact that you weren't told what form, so you have to make a guess. It would balance very nicely if you ended up with 2 hydroxide ions on the right hand side. This is a good example of a case where it's fairly obvious where you have to put in the OH ions. So, first of all, you're not looking at ammonia, because ammonia is going to be your thingy. If it's stated that hydrogen peroxide is the person that's doing the oxidation, it's oxidizing your hexamine cobalt, that means that's going to be your oxidizing agent, which means that's going to be the thing that gets reduced. So when you're doing the reducing, first of all, hydrogen peroxide is written as H2O2 and it's getting reduced. Reduced to what exactly? You don't know. However, you can make a fairly obvious assumption to what it can turn into by just checking it out. So you have H2 and O2, and if you write in that it's going to be oxidized, then reduced, it's going to gain an electron. And guess what? 2OH minus has the same amount of electrons and atoms as H2O2. Just not the same number of electrons, so you add in that 2E plus on the other side, which makes sense because it's gaining electrons. Now combining the half equations, you just want to multiply this top equation by 2, add them in, have anything that's common on both sides? Nope, so that's going to be it. Now the oxidation of iron to hydroxide by air. So if you add in sodium hydroxide to a solution of iron 2 compound, you get a green precipitate of iron 2 hydroxide. So again, sodium NaOH solution to an iron 2 compound. Okay, we're reacting those together and we're having the reactant of iron 2 hydroxide. That's going to be your reactant. So usually, okay, this before text is usually just saying what's the situation, how are we reaching, just a bit of context into how we're actually getting this, because it's easy to ignore that and be kind of lost when you're actually doing these experiments. Where are we getting these iron 2 hydroxides from, especially when it's an ion? These don't come in out of nowhere. You get these by reacting certain things together. So when we react the iron 2 compound with that sodium NaOH solution, because iron 2 is pretty easy to get on its own, sodium hydroxide as solution is pretty easy to get on its own, but iron 2 hydroxide is only, you don't just get that from nature. So you're gonna get that green precipitate, and that's the thing that's gonna be oxidized by oxygen in the air to an orange brown precipitate of iron 3 hydroxide. Okay, so again, we're getting that iron 2 turned to iron 3, and we're getting that oxygen being the oxidizing agent, so your air is being reduced. Okay, so half equation for the iron 2 to iron 3 is pretty straightforward. You can write what you know, which is FeOH2 to FeOH3. Obviously need another hydroxide ion, okay, because of course there's OH2 over here, OH3 over here, so you need an OH on the left side. If you have 1 minus over here and none over there, that means you 1 minus over here, and that's going to be it. No, half equation for oxygen isn't so easy. You don't know what it is being formed. What happens when you reduce air? True, right? It's not easy to understand. So it's not easy whether you need to balance the oxygens by adding water molecules or hydroxide ions to the right side. Okay, treat it as if it was being under acidic conditions, and the problem disappears. In this case, you only balance the oxygens by adding water molecules, because again, you need O's on the right side, okay? And you need to also lose electrons on the right side. I mean, you also need to lose electrons here, and as a result have a compound where the oxygen has lost electrons on the right side. The best way to do that is by adding water. Just think about atoms first, don't think about charge. We're just balancing the oxygen by adding water, as you would do if it was under acidic conditions. So now you have 2H2O, and then of course you need some more hydrogens, so you add that 4H plus on the left side. Then balance the charges by adding 4 electrons to the left side, so you have 4 negative and 4 positive, and as the right side has no charges whatsoever. Now that you have a perfectly balanced half equation, the problem is that it's under acidic conditions, so you're not going to have any H plus ions. In this case, we should have alkaline conditions with hydroxide ions. So get rid of the hydrogen ions and add enough OH ions to both sides so that you can neutralize both hydrogen ions. Because it's now a balanced equation, you must add the same number to both sides to maintain the balance. So again, we have 4H plus, so you add 4OH minus. Why do we add 4OH minus? Is because we add enough hydroxide ions to both sides so that you can neutralize all the hydrogen ions. If you have 4H plus and 4OH minus, we can get a total of 4H2O, correct? So you also had 4H minus on the left side, on the right side, so they turn into 4 water molecules on the left side, and that stays as 4OH minus. And then notice how the charges are still perfect. The water molecules are on the both sides of the equation. This is perfectly balanced. 2H2 and 4H2. Hold on. Sorry. You have 2 H2Os on both sides. You're gonna cut this H2O out. Get that 2 H2O on this left side. Check if the charges stay the same, which they are. And it's a bit tedious, but it's worked. It's worked. Now don't forget to recheck everything balances now that you've finished. O2 on the left side. Nothing on the right side. Actually no, shut up. There is stuff on the right side. 2 O's, 2 O's, 4 O's, 4 H's, 4 H's, bam, 4 negative charges, 4 negative charges, bam, bam, bam. Now you combine them. So you have that FeOH2 plus OH minus FeO. Check out the electrons, multiply the top by 4, add in the stuff. Is there anything that's common? Well, we have OH on both sides, so remove your OH on both sides, and you're done. That's going to be your final thing. Okay. Yeah, it is kind of funny that OH minuses actually don't even appear on the final ionic equation, although you're adding so many OH ions, in both the um, oxidation of OH2 and also the reduction of the hold on, the reduction of O2 and also the oxidation of the iron 2 hydroxide. So it's pretty funny. Now the reduction of manganate via manganate 7 ions to manganate 5 ions. So it's going to be gaining electrons by hydroxide ions. So it's literally just said that it's going to be hydroxide ions that's going to be reducing it. So it's a fairly obscure reaction, but it's not too difficult to work out and balance. It's unusual in the sense that hydroxide ions are acting as reducing agents. Usually it's another element, but this time we're having the hydroxide ions itself. Dark purple potassium manganate solution is slowly reduced to dark green potassium manganate solution by concentrated potassium hydroxide solution. So your OH ions are going to be coming from your potassium hydroxide solution. Bubbles of oxygen gas are also given off. So, unless the potassium manganate solution is very dilute, its strong purple color tends to mask the green potassium manganate in the short term. I'm gonna drink some water because my throat is killing me. Yeah, alright, my fault, man. I've been gone for a while. Let's continue. So now we're talking about manganate ions. Did we talk about? Yeah. So we talked about gas being produced. And your original solution is going to be dark purple, and it's going to contain potassium. It's going to contain manganate, and it's reduced to a green colored potassium manganate. And it's from VI to VII to VI, so it's actually gaining electrons. Okay. Well, actually, no, wait, rather. Is it? VII is gonna be your IV is 4, VI is gonna be 6, VII is 7. It's gonna be 7 plus to 6 plus. Oh, okay. Well, it's none of those, but I mean, as long as you know their formulae. And it's also not, what's manganate both ways? Anyways, I'm an idiot, so I guess it doesn't really matter. Okay, here we go. So we have, it's being reduced. So it's gonna go from a minus to a -2, and we can put in that minus E in the middle. Now, what's actually happening to the hydroxide ions as we turn them into oxygen gas? Because, of course, we're seeing that bubbles of oxygen gas are being given off, and we know that, your OH ions are being reduced. So, or your OH ions are being oxidized. So, what's actually happening to the hydroxide ions? It's actually very difficult to actually work out the half equation directly, but suppose you want to avoid thinking, just go through the standard routine. Write down what you know, 2OH, and you write down the oxygens and you balance it. So, your 2OH, balancing the oxygens in the process, you know that it's 2OH minus 2O2. So you want to balance the oxygens, so you're putting that 2 on the OH minus. So then you balance the hydrogens by putting the 2H plus. And then you balance the charges, minus on the left and plus on the right. So you, 2 plus on the right. So you put in, 2 minus on the left, 2 plus on the right. So you put in the, what's going on here? Why do you need to 4E on the minus? 4E minus on the right, because it seems to be perfectly fine. The reason is because am I tripping? This is 2 minus, this is 2 plus. Oh, okay, sorry. This is 2 plus. So you need 4E minus to reach this 2 minus on this side as well. My fault. So now you get rid of the hydrogen ions by adding, because, you don't have, wait, hold on. You have, because you don't have hydrogen ions, because this is an acidic, this is an alkaline situation. So you remove the hydrogen ions and then add enough hydroxide ions to neutralize the 2OH plus on both sides. So you add 2OH minus and 2OH minus. That's resulting in 4H minus and 2H2O, O2, 4E minus, and you combine them. So you have MnO4, E plus, MnO4, 2 minus, and you have your 4H, this, blah blah blah, E and 4, so multiply the top by 4, and then you get 4 MnO4 minus, 4OH minus, 4 MnO4, 2 minus, 2H2O, and O2. Nothing is repeating, so done. And the chemistry may be unfamiliar, but working it out is easy. So again, if you want to balance your OH, this is what's going to have to happen. Of course, it's going to turn into O2 as given in this situation. And so you first add in that hydrogen. After you add in that hydrogen, of course, you're not going to add in the oxygen because the oxygens are already balanced. So you add in that hydrogen. After you add in that hydrogen, you want to then add in the electrons. After adding the electrons, replace the hydrogens with the OH, and you're good to go. A little quick reminder for why we're adding an OH. Why is this an alkaline solution? Is because we're having potassium hydroxide, which is a base. That's going to be the solution. That's going to be the reducing, the oxidizing agent. So that's going to be, that's going to be the reducing agent. We're saying the reduction of manganate ions to manganate ions to manganate ions by hydroxide ions, which means that hydroxide ions are going to be your reducing agent. Okay? And of course, your hydroxide ions are going to be the things that are getting oxidized. As you can see, it's going to be gaining, so it's going to be losing those electrons. It's going to be losing them because you have a minus, and now you've turned it to a neutral. So next one, we have oxidation of chromium 3 to chromium 5. So of course, you can see that it's losing electrons because it goes from 3 plus to 5 plus. Or as you can imagine from the 3 to 5 number. Of course, the charge on the actual formula will differ. However, is my pun showing up? I think it is. Yes, it is. So let's just hold on, because I'm getting kind of bored. I'm feeling a little shy. I like the chromium. Chromium is my favorite. It was a good band, Chromium. It's a pretty good band. I listened to it for a while. But anyways, so if you add an excess of sodium hydroxide solution, that's going to be your solvent, to a solution containing chromium 3 ions, that's going to be another solvent. Adding those two solids together, well, you're getting that final result having, a complex ion hexahydroxychromate. That sounds awesome. Now, this can be oxidized by chromate Vi ions, can be oxidized to chromate Vi by warming it with hydrogen peroxide. So first of all, how are we getting yellow chromate V ions? By oxidizing hexahydrochromate containing your chromate 3 ions, chromium 3 ions. So you're getting chromium 3, you're getting chromate 6 from chromium 3 from mixing the chromium by adding an excess of NaOH solution to a mixture containing chromium 3 ions. Okay, so yes, there you go. Of course, your oxidizing agent is going to be your hydrogen peroxide, and your reducing agent is going to be your yellow chromate. Now, your chromate 3. So now we've already worked out the hydrogen peroxide half equation where it's acting as an oxidizing agent under alkaline conditions. We have H2O2. We've already done this in the previous question, but if you'd like to review it, we have H2O2, and you don't know what it's going to form, but you do know that it's going to be OH minus, and it's going to be OH minus since there's 2 over here, so you can write 2OH minus. 2OH minus, that's 2 negative over here, so you can add in a 2 negative over here, and there you go. Now this time, we just need to put together the half equation for chromium ions. What we do know is that it's losing 1 electron as it goes from here to here, and there's some differences in H and O's. Now this isn't the least bit obvious where to put the hydroxide ions to the water molecules. So let's just treat it as if it was done under acid by adding hydrogens instead. So first, noticing that there's 6 oxygens on the left side, let's add in 2 oxygens on the right side. So we add in 2 waters on the right side. After getting the 2 waters on the right side, Now you balance the hydrogens by adding, well, as you can see, there's going to be 4 hydrogens over here, still 6 hydrogens over here, so adding the 2 hydrogens on the right side. Now you balance the charges, you got 2 negative over here, 2 positive over here, so 2 negative, 2 positive, there's a total 0 on the right side, and you have a total 3 negatives, so you're adding the 3 electrons on the right side. We're adding everything on the right side in this equation. Finally, convert from acidic to alkaline by putting that 2H into OH, so we put in that 2OH minus, okay? I'm putting that 2OH minus on the other side. As a result, you're getting H2O on the right side, four of them, because you're adding these 2 to these 2, and you're getting 2OH staying as 2OH minus on the left side, and we have that as it is. Now we have the 2 half equations. Simply, as you can see, there's 2E and 3E, so multiply this by 3, this by 2, and as a result, you get 3H2O2 plus your 3, your chromate, what is your chromate? 3s? Yep. And these are chromate 6s. So then so you have 3 of them, 2 of them, and 4 of them. And is there anything repeating? Yep, you have your OH ions on both sides.
Okay.
Study. Study. Oh my god, headphone is the problem. Okay. Oregano. Please, just be happy. Okay, man, I'm sorry. 4H, 6OH, so you want to subtract 4 from the side, get 2 on the other side. H2Os are not repeating, CR, there's nothing repeating, so that's it. It's going to be everything that you need. And finally, we can go back into all of alcohols. Finally, right? Finally. Wait, hold on. Okay, so back to actually talking about oxidation of alcohols. Okay. So we're looking at, if I just could erase all this bullshit that I wrote last time, because honestly I don't think I knew what I was talking about. Okay, maybe I did. Maybe a little bit. Yeah, so we're having oxidation of alcohols using acidified sodium or potassium dichromate. Actually, we looked at this before. Oh, dude, they're already giving us the half equation. Yeah, dude, we've looked at this before. We literally looked at this over here. Would this be an acidified? Yeah, acidified sulfuric acid. So if you go over here, right here. No, wait. Yep, there you go. This is it. I believe. So yeah. Now, just reading through this again. Primary, hold on. So primary alcohols can be oxidized to either aldehydes or carboxylic acids depending on the reaction conditions. So yes, that means that the control variable will be primary. Aldehyde is going to be your aldehyde, or carboxylic acid is going to be your your dependent variable, and reaction condition is going to be independent variable. In the case of carboxylic acid that's forming, the alcohol is first oxidized to an aldehyde, which is then further oxidized to acid. Now if you partially oxidize your primary alcohol, then you'll get 2 aldehydes, correct? Now if you use an excess of alcohol, you can distill off the aldehyde as soon as it forms, then you can get it. Therefore you're doing 2 things here. First, you're putting in 1. One is that the excess of alcohol means that there isn't enough oxidizing agent present to carry out the second stage. And what is the oxidizing agent here? Well, as you can see, this is being reduced because it's gaining electrons, and that means that the thing that's getting oxidized is the thing that's losing electrons. Well, as we can see, if the dichromate is being reduced, right? Then what's being oxidized? What's being oxidized by? Sulfuric acid? See, it's being reduced. That means it is the oxidizing agent. So that means that if you put in excess of alcohol, that means that there's not going to be enough oxidizing agent to carry out the second step. It's going to all get run out just by doing the alcohol, not even by doing the aldehyde, correct? So that means, because truly what's happening is that after your aldehyde is formed, your aldehyde is then reacting with your alcohol. Your aldehyde is reacting. It's being oxidized to aldehyde or carboxyl. The formation of carboxylic acid. The alcohol is first oxidized to aldehyde. And again, what is the oxidizing agent here? Oxidizing agent is chromium. So if the alcohol is oxidized by chromium, then further oxidized to carboxylic acid by chromium, therefore the aldehyde is being oxidized, the alcohol is being oxidized. Therefore, if you put an excess of alcohol, that means the oxidizing agent, aka the chromium, will be finished just by using it on the alcohol. That's one. Two is if you remove the aldehyde, then there's no chance of it being oxidized anyway. Now the full equation is complicated, not really, but we get the final equation like this. And in organic chemistry, we like to simplify it and try to focus on what's actually being happening. And oxidizing and O from an oxidizing agent is represented. So as we know that since the Cr2O7 is the oxidizing agent, right? We can put in the O as the we can put in the O from that oxidizing agent to be replaced as represented as that, which would produce a much simpler equation. It also helps remembering what happens. You can draw simple structures in to show that the relationship between the primary alcohol and the aldehyde formed. So over here we have the O, which is the thing that actually truly reacts. It's the oxidizing agent, and it reacts with the two H's of the alcohol. One H coming from the actual OH group and another H coming from the alkyl group. As a result, we'll form a double bond with the C and an H2O. So the two H's form a bond with the thing, and then so as a result, we'll get that lone pair being then used for a beautiful thing called a double bond. Now, it's not intended to suggest any sort of mechanism for this reaction. It's just a way of. This is not intended to suggest any sort of mechanism for this reaction. It's just a simple way to help you understand or remember what happens. If you are in the UK level system, it is highly likely that your examiners will accept equations using that oxidizing agent. Consult syllabus, whatever, and yeah. Now, is there any mechanisms that we're gonna have to show for this? That's kind of crazy. There isn't. I swear there would be. I guess I can Google it. So anyways, so that's kind of what's happening. We can kind of imagine it as that, you have your O, you have your H. It forms from the H, from the two H's, one from the alkyl and one from the, and as a result you have double bond with the C, and you have H2O. Simple as that. Now, full oxidation to carboxylic acids. So now you're having the aldehydes being oxidized by your chromium, correct? And as a result, you have forming your carboxylic acid. Now, the full oxidation of ethanol to ethanoic acid is this. Well, so it's the original starting position, and as it goes on, you're having your ethanoic acid, your your reduced chromium, and 11 molecules of water. How have we gone through this is my question. Yes, we did. But we only stopped. Oh, wait, hold on. No, we looked at this exact example of it fully being oxidized, but not partially oxidized. Interesting. Okay. Now, again, you want a simpler way. So you want a simpler version because the oxidizing agent actually looks quite complicated. So let's make the oxidizing agent look simpler using that. And alternatively, you can write some separate equations for the stages of the reaction. So, as in writing it as the partial and then the full. So we're writing, first the normal equation like this. Should we write the CHO? Yes, we did. So that's going to be your first step, right? After you get that step, then your CHO plus your O giving you nothing but your carboxylic acid. Okay. But do remember that we are not including actually the rest of the oxidizing agent. Okay. But that's going to be that might matter. Probably will matter. So again, it's the first formation of ethanol, which is going to be your aldehyde, alde, and then it's your subsequent oxidation of the aldehyde into your ketone. No, your COOH. Okay, now your secondary alcohols. See, that's going to be your first primary alcohol. Remember, primary alcohols, PAs, go from your actual alcohol to your aldehyde to your COOH, right? Or you could write aldehydes as C double bond OH. CHO. Now, secondary alcohols are oxidized to ketones, and that's it. It's straight from the alcohol straight to the ketone. For example, if you heat up the secondary alcohol propane-2-ol, as in propane-2-ol, as it's the little guy, the alkyl group that's attached to the OH group is bonded to two other things, as you can see over here. This carbon is bonded to two others, here and here. In the primary, it was simply, forget about this. Imagine this was an H, and again, that would just be your propanol. Rather, that would just be your ethanol, right? So yes, this is pretty much it. Playing around with the, if you heat it up with sodium or potassium dichromate, we're using dichromate V solution again, acidified with the same kind of acid, you get propanol formed. Simple as that. Playing around with the reaction conditions make no difference whatsoever to the product. It's always going to be that. Using the simple version of this equation, you can show the relationship. It's the same exact thing to form water, okay? And you're getting the ketone at the end because you have a CH2 bonded to two C's, which is bonded to the double bond O. Now if you look back at the second stage of the primary alcohol reaction, you'll see that the oxygen is slotted in between the carbon and the hydrogen in the aldehyde group, produce the carboxylic acid. Second stage of the primary alcohol where it gets further oxidized and oxygen is slotted in between the carbon and the hydrogen. Oh, well, I actually didn't even read this. But yes, the O is just put in right there. So that's slotted in. You just slotted in that oxygen and to produce that carboxylic acid. In this case, there is no such hydrogen and that reaction has nowhere further to go. Yes, so since there is no place for that O, if there is another O that comes in, right? And if there is no place for that O to go, therefore there is no reaction that's going to happen, and you finish at propanol. Now if you have your tertiary alcohols, okay, this is going to be your branch. It's going to be bonded to three other alkyl groups, okay? they aren't oxidized by acidified sodium or potassium dichromate solution. There is no reaction whatsoever. If you look at what's happening with the primary and secondary alcohols, you'll see that the oxidizing agent is removing the hydrogen from the OH group. It's always the OH group and an H from an alkyl group that's being used. You know, it's not any H group. It's not any alkyl group. It's the H from an alkyl group of a carbon atom that's attached to the OH directly. It's the adjacent. It is going to be the alkyl group that's bonded to the OH, whose H bonds you're taking. Okay. But unfortunately, tertiary alcohols don't have any hydrogen atom like that. If you look at this, the carbon has no hydrogen atoms that can be taken. And in order to remove these two particular hydrogen atoms, you'll need to set up a carbon-carbon double bond first. Okay? As in, what it's trying to say is that if I wanted, a tertiary to happen, what I would need is this: CH3 double bond C OH, okay, resulting in 1, 2, 3, and then another CH3, or rather we'll make this an H. We'll make this a CH3. Hold on. No. It's forming this. You'll need to remove those two particular hydrogen atoms in order to set up sorry. In order for the double bond in the C double bond O, CH3. See, you might see that, okay, fine, yeah, your CH3. Why can't we just simply remove this hydrogen and form this double bond? Well, that's the problem. You need to remove two particular hydrogen atoms in order for that double bond to happen. You need to remove this hydrogen atom and a hydrogen atom for something else. However, the carbon doesn't have that hydrogen atom. The reason why we need to remove it from this specific carbon is because we want a carbon double bond between this carbon and the O. It can't be this. If we remove it from this, then again we would just be forming a double bond with this. That would make it nothing. We need it for this specific carbon. And if that has no hydrogens, then it's impossible, unfortunately. Now, if you use these reactions as a test for different types of alcohol, as we stated at first, first you need to mention or need to be sure that you actually have an alcohol testing for an OH group. You need to show that it's a neutral liquid free of water and that can be reacted with phosphorus V chloride to produce a burst of acidic steamy hydrochloric fumes. Okay, you will find the chemistry of phosphoric V test, but I don't really care about that right now. So you're gonna start off. Make sure it has no water, and it's neutral liquid. It doesn't have any H plus ions. It doesn't have any OH minus ions. And when you react it with phosphorus V chloride, it produces steamy HCl fumes. Okay. Now you would then add drops of alcohol to the test tube containing potassium dichromate with dilute sulfuric acid, which would be warmed in a hot steamy bath. A hot water bath. As in a practical environment, we would finally, after proving this, then we would just drop a few drops of alcohol into a test tube, into that, so that then we can use that to form, hold on. Different types of alcohol. I see. Okay, so listen. We're putting it into a hot water bath using these conditions. Now, these conditions look familiar. These are the conditions that's used for the ketone reaction, for the aldehyde to COOH reaction, and for the no reaction when it was a tertiary. Of course, this was when it was a secondary, and this one was when it was a primary. Okay. So then you can find out the various kinds of alcohol by just simply seeing what's the color change. If, in case of primary and secondary alcohol, the color solution turns to green. With tertiary, there is no color change. Distinguishing between the primary and secondary alcohols is therefore you need to produce enough of this aldehyde from the oxidation of the primary alcohol or ketone from the secondary alcohol to be able to test them. there are various things which an aldehyde can do which ketones just can't. So, of course, they're talking about just not the further oxidation. They're just talking about the partial oxidation. We're not bringing them all the way to COH. Okay? And so, these includes the reactions with Tollman's reagent, Felling's solution, and Benedict's solution, and are covered on a separate page. These are very important, and I will have to read through them. In my experience, these tests can be a bit of a bother to carry out, and the results aren't always as clear-cut as the books say. A much simpler but fairly reliable test is to use Schiff's reagent. Schiff's reagent isn't specifically mentioned in any of the UK syllabus, but it's the one that I always have used. Schiff's reagent is fuchsin dye decolorized by passing sulfur dioxide through it. In the presence of even small amounts of aldehyde, it turns a bright magenta. It must, however, be absolutely cold because ketones react with it very slowly if you get to give the same color. If you heat it, obviously the reaction will be faster, the change will be faster and potentially confusing. While you are warming the reaction mixture in the hot water bath, you can pass any vapors produced through some Schiff's reagent. That's kind of confusing, but it's okay. Oh, they go hard on Schiff's reagent. Okay. Let me talk about esterification. Now, is esterification actually in our syllabus? I'm not sure. I'll have to check. Most probably though. Hopefully they don't go too hard on this. On this. Huh? Not sure. I think it's about them. Right now. Aldehydes, ketones, hydration of ethene. What is this talking about? Hydration of ethene? Mechanism for hydration of ethene. When did we do this? Oh my god, I don't even remember. Hydration of ethene to make ethanol. I don't even remember this. That's concerning. Dude, I printed this. Where is it? Alright. So what we're actually doing here is actually oxidizing your aldehydes and ketones, correct? Because, simply we said that, first we were just passing them through, what was here? So first we were actually, after what we truly did here was we put in the dichromate, right? And so we oxidized our primary and secondary alcohol into an aldehyde and ketone, correct? And then you need separate tests using Tollman's reagent, Felling's solution, and Benedict's solution. So that falls under oxidation of them. These look at ways of distinguishing between aldehydes and ketones using oxidizing agents. So further oxidizing agents. So you're further oxidizing your aldehydes and ketones using your original potassium dichromate solution, Tollman's reagent, Felling's solution, Benedict's solution, blah blah blah. Now, first of all, why do they behave differently? The main difference is because of the presence of the hydrogen atom attached to the CO double bond in the aldehyde. Ketones don't have that. And the presence of that hydrogen atom makes aldehydes very easy to oxidize. Or put another way, they are very strong reducing agents. I mean, I kind of can imagine this as since there's an H. Let's see this. Oxidizing agent is a substance which oxidizes something else. Reducing agent is something that removes oxygen from something else. Oh my god. Oxidizing agents give oxygen or remove hydrogen. Reducing agents remove oxygen from another substance and give hydrogen to it. Yeesh. Okay. So simply put, as we have a hydrogen atom over there, as we know, it's literally taken, see the aldehyde is already formed. However, when we have another O, right, that H can be taken away. And if that H is taken away, then is it being reduced? Well, is it reducing something else? Well, it's helping that gain an hydrogen, which means that if it's gaining a hydrogen, therefore, that's counting as reducing them. Yeah. If something else gains hydrogen, you're reducing them. Okay, so because ketones don't have that particular hydrogen, they are resistant to oxidation. As in, since they are a reducing agent, that means they get oxidized. So since ketones don't have that H atom, they aren't not only are they not good reducing agents, but they are also resistant to oxidation. Not only very strong oxidizing agents like potassium manganate solution can oxidize ketones, and they do it in a very destructive way, breaking the carbon-carbon bonds. So provided you avoid using these powerful oxidizing agents, you can definitely tell the difference between aldehyde and ketone. Aldehydes can be easily oxidized by all sorts of oxidizing agents, but ketones aren't. So, what is formed when aldehyde is oxidized? Well, it's going to be your carboxylic acid. But rather, it depends on whether it's done under acidic or alkaline conditions. If under acidic conditions, the aldehyde is oxidized to carboxylic acid. Under alkaline, this couldn't form because it would be reacting with the alkali. A salt is formed instead. In the case of methanol HCHO, the oxidation goes further. The methanoic acid or methanoate ions are easily oxidized into carbon dioxide and water. What song is this? God damn, this is so good. Alright, sorry about that. My ears hurt like a lot. So, when you're oxidizing these, I would like to think of it as you're having, your alkaline conditions. You're having an OH reacting with this. As a result, you're getting H2O that's forming here. So you're having RC double bond O, single bond over here, single bond over here. O with two H's. Okay. Then you have another O that takes these two, leaving O negative as that. That's how I'd like to imagine it. Okay, now building your equations for oxidation reactions, right? So how are we gonna do that? You need to only work out. If you need to work out the reactions for these reactions, the equations for these reactions, the only reliable way of building them is to use electron half equations. The half equation for oxidation is obviously varying depending on whether you're using the acidic or alkaline conditions. Under acidic, it's going to be simple. It's going to be this plus water. It needs this, does this. Um, it's literally just the acidic conditions, but you replace the H with the OH. I mean, not, sorry, you just add in plus 2 OH minus. So now you have 2H2O, and you have two H2O, and then, sorry, 2 OH minus. Sorry, 2 OH minus. Sorry. And then forming H2O. This is gonna form 2 H2O. And H2O, this cuts. This somehow stays. Is this unbalanced? Okay, I think it's an entirely different reaction then. You can't really think of it like that. I just don't understand this reaction. I'm not understanding this either. What is going on? I literally just did this. Yikes. Bro, we literally did redox reactions under alkaline conditions as well. Rather, we're doing peroxide. And this time we're using an aldehyde rather than anything else. What is our going to be our oxidation agent? Hold on. Is our oxidation agent? Oops. So oxidation agent can be one or the other. Like it can be weak, it can be strong, it doesn't matter. But by the end of it, under acidic conditions, you're having I don't know what the that makes this kind of annoying because I don't know how to derive this specific equation, mainly because I don't know what the oxidation agent is. Or perhaps I'm really stupid and I can't see it. Whatevs. These following half equations are combined with the half equations from whatever oxidizing agent you're using. Oh, because the oxidizing agent is in of itself gets separated. Oh my god, dude, I'm such an idiot. Okay, so we know that RCHO, oh my god, we know that RCHO turns into RCOH, correct? And then you just do everything. So, your CHO, COOH, so we're gonna need H2O on the left side to fill in that missing O, Now we have H2 on this side, so we added 2 H's over here. Then we added 2 electrons to balance out the 0, 0 charge. And then in the other one, we have RCHO to RCOO minus, because it forms, sorry, am I tripping? It forms a carboxylic salt. Oh, by the way, before we continue, I just wanted to know, there was a mechanism for one reaction which I just didn't really question. Yeah. Wait, is there anything mechanism of primary alcohol and aldehyde, and there's a primary alcohol and oxidizing agent? Alcohol oxidation, you have your primary and it turns into your R double bond C double bond O bond H, oxidize it again, forming a carboxylic acid, but that's not really showing the mechanism. Mechanism for chromic acid oxidation. No, so here we have Cr. You're bonding an OH group. This OH group has 2 lone pairs. Well, I suppose. Wait, am I an idiot actually? Is it supposed to have 2 lone pairs? Oh my god. When you're thinking, just know this stuff. One lone pair goes to CR. Okay, this is not oxidation. Wait, no, dude. Mechanism oxidation of carboxylic acid. Addition of a molecule of water to the aldehyde followed by second oxidation. So we have first your, oh my god, my phone ran out of charge? No, it's a normal clock. So we have your R double bond OH, that's gonna be your aldehyde. Then you add it with a water, forms the aldehyde hydrate, which is gonna be your OH. Okay, I'm sorry, I'm just gonna because I want to draw with this as well. Right, so this is what I'm seeing. What is going on with the text in the back? That is so trippy. Okay, wait. This is too much. Maybe I can make it like bigger. That was a lot of types. Yo, you can get it like that. Dude, this is like honestly the best app like ever. Like props to the people who made this app. It is so good. Like genuinely it is amazing. Ah, dang. Alright. So let's close this. I feel like this is such a crazy app. Alright. So we're having, this is what we're focusing on. Right. So after putting that water in, right? So if, let's say we have here O. Okay, you're just adding that oxygen, and as a result, you're getting an OH and an HO with 2 lone pairs and an H to this. The lone pair is gone. Wait, okay, where are we going with this? And somehow this turns into a double bond O, bond OH. But that's not even a... Oh, that is a carboxylic acid. Bro, wait, hold on, what? Is this a bit too advanced? I feel like this is. Okay, I have to first be able to understand why is this turning into okay. So this is going to be slightly negative. This is going to be slightly negative. This is going to be slightly positive. So is it that this goes here? Or like this takes an electron and this forms a bond like this, which forms an
Hi there, thank you for listening to this song. Please join us on our Facebook music page and our YouTube channel. We hope you have a great day.
You too, man. So this is breaking, forming another bond here. Okay, so now, whoops, what am I doing? Okay, so, okay, now the O is going to be positive because it was bonded to 2, and now that that electron is gone to this H. Why is this happening? Since it's gone to this H, okay, it's because of that. Since it's gone to the H, that means this is now slightly positive, and you still have your O that's going to be containing your like this. And this is going to be slightly positive, this is going to be slightly negative. That this goes into this and forms a bond with this. I have no idea. Then you have OH, and that this just forms a bond with this. So then you have O, two lone pairs and an H. I have no idea. But anyways, now that you have your H with an O with two lone pairs, then it forms a bond with another Cr. This is going to be your oxidizing agent, right? And as a result, it forms this monstrosity. But in reality, all this is that it's taking your what's happening here? O becomes plus. CrOH O double bond. So it's gaining, or it's forming a bond, and it's taking a hydrogen. Sorry, no. Okay, look. It breaks a double bond with the O and gets a hydrogen, and also forms a bond with the O. This oxygen is the oxygen with two lone pairs and hydrogen attached. This is the hydrogen and the H, the OH and the H, which are down here. So the oxygen uses one pair to form a bond with the Cr. And where did the OH come from? You still have your OH and your H. Alright, we're confusing ourselves. This is something I'll ask my teacher. The prof. Okay, let's keep it simple. That's such a good song. Yeah. So you're having RCHO, 2 RCO, 2 oxygens, so you want to move oxygen over here. Sorry. What are we doing? Two oxygens over here, 1 oxygen over here. So get 1 water over here. Now you have 1 water over here. Imagine these weren't there, right? So now you have 2 hydrogens over here, 3 hydrogens over there. So we'll need 3 hydrogens, so we have 3H2O, 3H plus. Now we have 3H plus, I think everything is done. The hydrogens are 1, 2, 3, 1, 2, 3. RCOs, we have 1 carbon, 1 carbon, 1 R, 1 R. OO, well we have 1 O here, and 1 O here, and we have 2 O's here. So then we have a plus, we have a minus, so that's a 0. No, sorry, 3 plus, and 1 minus, that's we have 2 minus over, we have 2 minus here, and we have 3 plus, 1 minus, that's 2 plus, so So that means we need to reach a 2 minus. Nope, we don't need to reach a 2 minus. We need to reach a much more than a 2 minus. We need to reach a, so the 3, oh sorry, no, hold on, I'm making a mistake. It's H2O minus, forget about this, that'll be 1 minus and 2 plus. That means you need to go down 3 minus, 3 minus. Are you sure? You have Cl minus and you have your 3H plus. And why do we need 3H plus? H2O? Wait, no. Oh, I'm losing my mind here. Let's just do it again. Okay. So this needs an H2O. This needs 1, 2, 3. Everything, all the atoms are balanced now. So now this is going to be 3 plus and 1 minus. So that's going to be 2 plus. This is going to be totally neutral. So it's going to have 2E minus. Now you want to replace all these with a 3OH minus and a 3OH minus, resulting in this forming 3H2O. And this cancelling out, this turning into a 2. So now you have 3OH minus, 2H2O and 2A minus. Yep, okay. Easy peasy. It's very easy to get confused when you have it already. These half equations are then combined, whatever, blah blah blah. Specific examples, assuming that you already know that you have either an aldehyde or a ketone. There are other things that you can get that can get positive results. There's a test for a carbon-carbon double bond, carbon-oxygen double bond in aldehydes and ketones. Oh god. But anyways, do I need to know that? This is the test. Oh god, what is that? What is that supposed to be? Oh my god, dude. That's too much information. Okay, this is going to stuff that is kind of meh. I'm so excited to do chromocarbs for next year, for this year. cool. Okay, I have just wasted my time. Okay, I just want to check out one more thing because there was one thing that really bugged me, and that was this. I don't know what this is. I swear I've done this before, but I just don't remember where did I see this. I why did I download this page? Is it because like all at the start we had a reaction for ethene or something? I remember doing something like that. Is it the reasons for the conditions over here? No. That was the mechanism. Oh, it is. It is. I see. Okay. And I did go to these. Okay, if I did go to these, then I think I can safely just watch that video then. However, I didn't really write anything, so I'm not really sure. Quickly going over that, it said that, you know, over here, we're having to make alcohols from alkenes. We need ethanol. So in this situation, you're doing ethanol from ethene. So you're going to use the catalyst, solid silicon dioxide coated with phosphoric B acid. So you have your alkene over here, or ethene specifically. Stop. You're gonna have your ethene over here, and your water. That's gonna be just reacting the ethene with steam. Then you have your. This is gonna be your catalyst. You know, your phosphoric B catalyst. It's gonna be your acid catalyst. Getting an alcohol in the end. Now the mechanism for this reaction is going to be displayed here. So you have a fact: ethene mixed with steam and passed over a catalyst will form, you know, ethane, not ethanol rather. These are going to be your conditions. And the mechanism for hydration of ethene assumes that we know electrolytic addition. So step 1, all the hydrogen atoms in the phosphoric B acid are fairly positively charged because they are all attached to negative oxygen. One of these hydrogens is strongly attached to the carbon-carbon double bond. So H breaks off from the O, makes O negative. That's going to turn this O into a phosphoric acid, if I'm not wrong. H is then bonded, double bond is broken, you have a positive carbocation. Step 2, carbocation is formed reacts with one of the lone pairs in a water molecule. Carbocation is one which carries a positive charge. Now the easier way of remembering this is that oxygen has to carry a positive charge if you're reacting a positive ion with a neutral molecule. This H2O is neutral, although it is a slight positive charge, slightly negative. In reality, this entire thing is still neutral. So when you react it with this, you'll still have a positive charge on the H2O. That means there has to be a positive charge somewhere. Another way you can think of it is now that you're reacting O with another thing, it's going to have a positive charge as the oxygen is reacted to 3 different elements, or 3 different atoms. Finally, H, so one of the hydrogens of the oxygen on the oxygen is removed, leaving it as one of the hydrogens is removed and bonds with the the phosphorus to form, it's phosphate. It's phosphate. This is dihydrogen phosphate. So then it forms the phosphoric acid, making this an alcohol. Okay, that's pretty easy. Just okay. Let's just go through this one last time. Okay, your alkene, it breaks, and you have the homolytic fission, and it goes H plus bonds with this to form your H bond with this alkane. Double bond is broken, forming. It's bound to two things. It needs one more bond, so it's positive over here. Now it's not going to bond with this, rather it bonds with H2O. Okay, it just goes in straight. Okay, doesn't matter how many doesn't matter how many electrons it has, because it's still going to form an H2O like that, and it's still going to have that positive on it. Well, the plus is going to be on the H2O now, and so we can draw that like this. Okay, and so when you're O with the negative charge this time, it's going to have a negative charge because the H over here broke off. Oh my days, man, it's not that deep. H breaks off, leaving this O with a negative charge. It gives O a lone pair, giving it a negative charge. Over here, that O with the lone pair comes back, meets with hydrogen again, kind of putting things back to where it was, leaving this molecule as a neutral, making this molecule, this bond as neutral as well, as this electron is put back into hydrogen, put back into usage of being used as a bond for hydrogen. So yeah, I don't know why we talked about that. We talked about that because it's not even a test for carbon-carbon double bond. It's just something that was bugging me. So so now we are looking at following examples. Assuming that we have either one or the other. In case a ketone does nothing, so that only an aldehyde will give a positive result. So that's really just it. So some examples are using solid acidified potassium dichromate. It's going to be a classic. Orange turns green, aka orange, aka potassium dichromate. Sorry. Aldehyde turns into COH, and your ketone doesn't change at all. Before we continue, they said what was the thing that was able to oxidize it? They said that potassium manganate V solution, permanganate solution, can oxidize ketones. They are very strong oxidizing agents. So over here, the reason why he wrote all of that, because we are able to formulate this, but we can read through it. Cr2O7, so we want one for the we want one for both. So this is the reaction for the oxidizing agent. This is the reaction for the actual aldehyde. So for oxidizing agent, it's turning into 2Cr3 plus. So it's gonna have this is gonna be with your sulfuric acid. So you need the 7 O's. That's gonna go 14 each, and so this is a total of 2 times 3 6, and this is a total of 14. So you need 6 to counterbalance, and your aldehyde is gonna go like this to this. So you need an H2 on this side, you need 2 H's on this side, you need 2 electrons on this side, giving the following equation. Now he has split everything rather than using symbols like O. The problem is that what is important in these reactions is the color change in the oxidizing agent. because that's how you determine. You have to explain, for example, why the solution turns green. Any equation that has to write, any equation that you want to explain with that has to show the production of common 3. If you aren't exactly sure how the two half equations are combined, okay. Now using Toland's reagent, the silver mirror test. Before we continue, I just want to see, after these two reagents, so where are we at? We are at esterification. Then we are talking about iodoform. Then we talk about uses. When it comes to our spec, okay, they are talking about forming iodoalkanes. So I don't know if that's iodoform. Let's see. Triiodomethane, which is like iodoalkanes. Presence of this group. Where's my call? Oh Allah. Concentrate phosphoric acid from alkenes by elimination. I cannot like recognize these, although I should be able to. Follow and understand the difference between those. I mean, see, the thing is, like, these are, like, I've done all of these, yet I still cannot, like, pinpoint, okay, like, oh, this is this, oh, this is this, oh, this is this. For some reason, I can't do that. What is the problem? Like, 50% this and this to produce bromoalkanes. For some reason, I just can't, like, understand that from the top of my head. Like, somewhere in my noggin, it's like, oh yeah, that probably makes sense. But I can't really, like, understand that right now. Something to do with solubility? That's what it was for halogen alkanes. Which bromoalkane is. Yeesh, man. Let's see, 50. If I just write control F50. Dang. Okay, well, it says here that, you know, when you replace the OH of hydrobromic acid, so rather than using hydrobromic acid, you get the hydrobromic acid by reacting a mixture of sodium and potassium and sulfuric. There is a reason for that, and that mixture is going to be 50-50, which reduces your hydrogen bromide. If I go to our academics, all of halogen alkanes, and then talk about our bromo so practical details further down the page. Okay, a mixture of red phosphorus and other bromine and iodine to form bromoalkanes and iodoalkanes. This is one of the reactions of an alcohol that's used to form bromo and iodoalkanes. To produce bromoalkanes, to produce iodoalkanes, red phosphorus and iodine, and 50% sulfuric acid and potassium bromide, sulfuric acid and 50% concentrated sulfuric acid and potassium bromide. It's because you need to form. The only time I read 50-50 was when you did the reaction, when you wanted the substitution or elimination reaction. Alright, TBH, what else? What else, man? This is getting out of hand. Okay, let's talk about tolerance reagent. So, this is this, and this is going to be your oxidation agent, right? And it's made, with the most important part, it's made from silver nitrate solution. You add a drop of sodium NaOH solution, it's always usually NaOH, so we put in that NaOH with that silver monoxide, then add enough dilute ammonia to redissolve the precipitate, and then you get this, okay? And then you add a few drops of the aldehyde or ketone onto the reagent, which is this again, and then warm gently in a hot water bath. No changes when it's ketone, and then aldehyde, the colorless, produce a gray precipitate of silver or silver mirror on the test tube. Now aldehydes reduce the other one to metallic silver because the solution is alkaline and the aldehyde itself is oxidized to salt, so salt of the corresponding carboxylic acid. So again, since the solution is alkaline, since this diamine silver is alkaline, okay, so it'll oxidize to form salt, the carboxylic acid salt, okay. So you have this and it gets formed just to form Ag, reduced to Ag. So you do it, you know. Hold on, what is this? The mall. Okay, I suppose it's given. I don't know what this is about, but this is, I suppose this is just a reaction. You know, you just form these two things, and so, you know, you're gonna have a plus over here and everything over here is neutral, so you're gonna have an E over here, combined with the other one, which is this to this. This you should be used to, giving us the form of the overall equation. Of course, we turn the H pluses into OH minuses over here, and you get this as your final equation. This will be your explanation. This equation that you use in the explanation of why it changes color into silver. Okay. Now, Fehling solution or Benedict solution are variants of essentially the same thing. Both contain copper 2 in an alkaline solution. Fehling solution contains copper 2 ions complex with tartrate ions in sodium hydroxide solution. Complexing copper 2 with tartrate ions prevents precipitation of copper 2. I don't know what the hell that means. What does complexing mean, dude? Benedict solution contains copper 2 ions complexed with citrate ions in sodium carbonate solution. Again, complexing the copper 2 ions prevents the formation of a precipitate. This time a copper 2 carbonate. So if we initially put in that copper 2, those copper 2 ions with the sodium hydroxide solution, then we would get a precipitate of copper hydroxide. But we complexed it with tartrate ions. So we complexed it with citrate ions to prevent the formation of a precipitate, whether it be a carbonate, whether it be a hydroxide. Both solutions are key because both solutions are used in the same way. Drops of aldehyde and ketone, and then warm gently in a hot water bath. No changes in the ketone. Blue solution produces dark red precipitate of copper 1. Aldehydes reduce the copper 2 to copper 1 because the solution is alcohol. The aldehyde itself is a salt. The equations of these are simplified to avoid writing in the formula of tartrate or citrate ions in the copper complexes. The electron half equations for both can be written as Cu2Cu in complex forming this copper oxide, and your RCHO with this. This is easy. Adding these together, you get this. If you're really alert, you might wonder where the hydroxide ions come from if we're talking about Benedict solution, which is made alkaline using sodium carbonate. Sodium carbonate solution is alkaline because the carbonate ions react reversibly with water to produce hydroxide ions and hydrogen carbonate ions. Again, when we're talking about Benedict solution, that shouldn't contain any OH ions, yet it's alkaline. So where are the OH ions coming from? It's made alkaline by using sodium carbonate so we're just looking at Benedict's here. Yeah. So since we're using sodium carbonate, see, now you might be wondering, where are the OH ions coming from in the Benedict solution? Well, the sodium carbonate that we put in will react. The sodium carbonate solution is alkaline because the carbonate ions in the sodium carbonate will react with the water to produce hydroxide ions. And the water is coming from the Benedict solution. What is the formula for the Benedict solution? What is the formula of Benedict solution? Did it already say it? I think I already mentioned that, no? No, I only mentioned that. In Benedict solution. Oh wow, I just talked about the formula of Benedict solution and it gave me the net reaction between aldehyde and the Benedict solution. That's hilarious. Carboxylate. Again, RCHO plus 2Cu2 plus 5OH, RCO plus Cu2O plus 3H2. I'm not really looking for that. I was just looking for what the formula of the Benedict solution was. Oh yeah, okay. It does contain water. There you go. So the water from the Benedict solution reacts with the sodium carbonate and the carbon ions in it to form hydroxide ions. And hydrogen carbon ions, but the OH ions are then used as the excess to form whatevs. Is that everything that we need to do for today? I think so, yeah. Esterification didn't really seem to come in our syllabus. And the rest that we learned was actually learned previously in previous chapters. There's obviously all these, which seem to be like paper 3 stuff, so yeah. Secondary alcohols to produce ketones, primary alcohols to produce carboxylic acids, Carboxylic acids also to produce aldehydes. Carboxylic primary alcohols. Oh my god, I'm so sleepy, guys. I'm sorry. Oxidizing agent can be represented as O. Very nice. Very nice. Cool, dude. This is great. Alright, I'll see you guys later.